Hi, I'm Paul Velleman, here to talk with you about random variables. Let's review the important ideas from this chapter. We'll look at expected value, standard deviation, working with means and variances, the Pythagorean theorem of statistics. First, let's talk about expected values. Whenever you buy insurance, you and the insurance company are both making a bet. You pay the company a premium, and if nothing bad happens, they keep it. If you get lucky and your house burns down or you die, you win. The insurance company pays you a lot of money. The company's payout on any given policy is a random variable whose value depends on what happens to the policyholder. While the company may lose money by making big payouts to a few people, they make a profit by keeping the premiums paid by most of their customers. Let's look at a simple example, a death and disability policy. Let's say there are three possible outcomes. The policyholder may die, become disabled, or survive the year unscathed. The policy will pay a death benefit of $10,000, a disability payout of $5,000, or, of course, nothing to most folks. The insurance company knows the probabilities of each of these outcomes. Let's suppose the death rate is 1 person in 1,000, and that another 2 in 1,000 suffer some kind of disability. That means the other 997 out of the 1,000 customers suffer neither fate. Now we have a probability model for the random variable. So we ask, what's the company's expected payout for these policies? The answer we need is the expected value of our random variable, written E of x. That's another way of talking about the model's mean, mu, the theoretical average payout for all policies. We can't find this average the old-fashioned way, though, because we're talking theoretically about all policies the company ever has sold or ever will. In a sense, n is infinite. Instead, we'll use the probability model. The company expects to pay out $10,000 on one policy in 1,000, plus another $5,000 on 2 of every 1,000 policies, plus nothing on the other 997 of 1,000 policies. That means their expected payout averages $20 on every policy they sell. How can the insurance company turn a profit? Well, all they have to do is charge policyholders more than $20 on each policy. We'll talk more about that answer in a few minutes. Right now, though, let's look carefully at how we calculated this mean. Here's the formula for the expected value. Each value of the random variable is multiplied by its probability. Then we sum them all. That's the expected value of the random variable x. It's also mu, the population mean. Of course, once we know the mean, we want to find the standard deviation too. That's the square root of the variance, as you've learned earlier in this course. To find the variance, we must find how much each value deviates from the mean. Then we square those deviations and average these squared deviations using the methods we just learned. We multiply each by the corresponding probability and add them up. There's the variance. One step to go. Find the square root, and voila, the standard deviation. Let's try it out on the insurance payouts. We found the insurance company's mean payout is $20. To find the variance, we subtract the mean from the first value of x, square the deviation, multiply by the probability, and then we add the terms for the other payouts. This gives us the variance. And now the square root tells us the standard deviation of the insurance company's payouts is about $387. Will the company make a profit? Well, the expected profit is the difference between the money they collect, the premiums, and the money they pay out. Suppose they charge customers a $50 premium for each policy. We already know their expected payout is $20 per policy, so the company can expect to make an average profit of $30 per policy. Well, when we add or subtract a constant, here the $50 per policy, that increases or decreases the mean accordingly. But shifting all those payouts by $50 has no effect on the spread, so the standard deviation is still the same. To summarize, what happens when we shift the values of a random variable? The expected value of x plus or minus a constant is simply the expected value of x, plus or minus that constant. The variance of x, plus or minus a constant, is the variance of x. These theorems deal with means and variances when adding a constant to a random variable. But what happens if we multiply by a constant? Suppose the company doubles the payouts for this policy. For death, the company now pays $20,000, for disability, $10,000, and otherwise, of course, still nothing. What are the mean payout and standard deviation for the new policy? For the original policy, the expected payout was $20. For the new payout policy, with all payouts doubled, the expected payout is, right, $40, also doubled. And the standard deviation? It was $386.78. Doubling each payout also doubles the spread, so the new standard deviation is twice as large. And the variance? Well, if the standard deviation is doubled, then before we took the square root, the variance must have been 2 squared, or 4 times as big. Let's look at the theorems. To summarize what happens when we rescale the values of a random variable, the expected value of a times x is just a times the expected value of x. But the variance of a times x is a squared times the variance of x. Now there's just one more situation to discuss, and this is the important one. Instead of doubling the value of a single policy, what happens if we look at 2 policyholders? What are the mean and standard deviation of the company's expected total payout for 2 independent policies? A word of warning. At first it may seem like 2 policies is just the same as doubling the payout for a single policy, but a little thought should convince you that it's not. For the doubled policy, possible payouts are $20,000, $10,000, or nothing. But for 2 independent policies, if both people die, there is a $20,000 payout. But 1 death and 1 disability cost the company $15,000. A death of only 1 policyholder totals $10,000, as would 2 disabilities, and so on. Here are the rest of the possibilities. Clearly, then, these 2 situations aren't the same. In statistics, the sum of 2 independent random variables is quite different from doubling a single outcome. So, how do we find the mean and standard deviation for the 2 policy case? Well, the mean is easy. The expected value of the total payout is simply the sum of the expected payouts. For 2 policyholders, then, the company expects to pay out $20 plus $20, or $40. In general, the expected value of the sum or difference of 2 random variables is the sum or difference of their individual expected values. Finding the standard deviation, though, is another story. You might think we'd just sum the standard deviations, but you'd be wrong. It's the variances that add. For the insurance policies, it works like this. The variance in the first payout is the standard deviation squared. We add the variance for the second policy to get the variance for the total payout. And the standard deviation? Well, that's just the square root. Does this process ring a bell? We sum 2 squares to find a third square, as in a squared plus b squared equals c squared? That's right. It's just the Pythagorean theorem. This process of adding variances is the Pythagorean theorem of statistics. And like the geometry version, there's a condition. In geometry, we can't apply the Pythagorean theorem unless it's a right triangle. In statistics, the random variables have to be independent. So, the theorem says the variance of x1 plus or minus x2 is the variance of x1 plus the variance of x2. Wait. We add the variances for the sum and for the difference too? Well, that's right. Think about it. Variance is a measure of uncertainty. Every time something happens at random, uncertainty increases. Each time we plan to add or subtract a random result, our uncertainty about the result increases. So we add the variances for the sum or for the difference of random variables, provided, of course, they're independent. There you have it, random variables in a nutshell. We've looked at expected value, standard deviation, theorems about means and variances, and the Pythagorean theorem of statistics. Pay careful attention to the Pythagorean theorem. As this course goes on, you'll encounter many places where you'll need to add variances. Thanks for watching.